concentration of CO2, that is, your tissue cells will probably have a fairly, CO2, not O2, that's a C there, will have a fairly high amount of carbon dioxide in it. Okay. And other wastes as well. Maybe urea if it's a liver cell or something like that. Okay. We also know that the blood coming in from the arteries has a fairly low concentration of carbon dioxide and wastes. So this blood coming in down here and the blood that's in the capillary has a low amount of CO2 and a low amount of wastes. All right, so far so good. Makes sense? So let's think about what's going to happen here. Earlier on in the semester, we learned about several different types of mechanisms that things can use to cross cell membranes, right? So one way that things can use to cross cell membranes is diffusion or facilitated diffusion. Which way do molecules move for diffusion? From low to high or high to low? High to low, right? So molecules will move from the side of the membrane where they're higher in concentration toward an area where there's a lower concentration. Now, whether it uses diffusion or facilitated diffusion depends on the particular molecule. Something like oxygen or carbon dioxide, those are small enough to cross membranes using simple diffusion. Facilitated diffusion would be for larger things like, say, an amino acid or a glucose molecule. But we'll just sort of lump those together and say diffusion, okay? Another force that can move things across membranes is osmosis. In fact, osmosis can almost work like a force or a pressure, causing water to move across membranes. And remember that water is going to move toward the side of the membrane where there's higher solute concentrations. And in this case, blood has a lot of solutes dissolved in it, so in the blood is going to be where we have higher solute concentrations. Okay? Another force that can move things across membranes in the capillaries is blood pressure itself. We've got this blood pressure pushing the contents of the blood out against these porous capillary walls, and so some things can actually be pushed right out by the force of blood pressure itself. So blood pressure is this force of the blood outward against the walls of the blood vessels, mainly because of heart contractions. Ventricles squeeze, push blood out there, and it's being pushed against the walls. Okay? So I want to add one more thing to my picture here, and then we should be able to figure out everything that's going on. The only thing that I don't have on here is osmotic pressure, or the pressure of osmosis moving water into the blood. And that's pretty much a constant force all along the capillaries. So I'm going to draw a couple of arrows here representing osmotic pressure, trying to push water inwards. Okay? So here we go. I bet you guys can figure out exactly what's going to happen. Let's take a look at oxygen first. Blood coming into the capillaries is a high concentration of oxygen. The blood that your heart sends out to your tissues under normal circumstances will have lots of oxygen in it. Your tissue cells have a very low amount of oxygen in them because it's constantly being depleted and used up by cell respiration. You guys know how diffusion works. Which way is the oxygen going to move? Is it going to go into the blood or out of the blood? What do you guys think? Who votes for into the blood? Who votes for out of the blood? Okay, good. You guys understand this. So, simply going to go from the side where it's higher in concentration toward the side where it's lower. Oxygen is going to move out of the capillaries and into the cells surrounding it. That's good, because those cells needed more oxygen to use up for cell respiration. Okay? Now, how about carbon dioxide? Blood that's arriving at your capillaries has a fairly low concentration of carbon dioxide. Your tissues are producing lots of excess carbon dioxide from cell respiration waste. Which way is carbon dioxide going to move? Who votes for into the capillaries? Who votes for out of the capillaries? Okay, good. You guys got that one too. From the side where it's higher toward the side where it's lower. So CO2, carbon dioxide, is going to move into the bloodstream at this point. Okay? How about nutrients like glucose and amino acids and so forth? Lots of them in the blood, not so much in the tissues because they're getting used up. Which direction do they go? Into the blood or out of the blood? Who votes for in? Who votes for out? Okay, good. This is easy enough. So there's lots of nutrients in here, lower amount here. Those things like amino acids and glucose and so forth are going to move out because of diffusion. So far, so good? Now, that's all fairly easy and pretty intuitive if you think about it. The cells need more oxygen so they can do cell respiration. They need more of these glucoses for energy and amino acids for protein building blocks. So those are going into the tissues. Tissues are happy. And they're getting rid of carbon dioxide. Oh, I forgot about the wastes here, which of course, I know you guys have figured this out. The wastes are also going to be going, other wastes, into the blood as well, going from high to low. But carbon dioxide and other wastes are going to be diffusing in. The cells are getting rid of those. Cells are happy. Now, there's one other funny little thing that goes on, and that's movement of water. So, water is moved by two different forces in this case. One is osmosis. Osmosis is trying to push water into the capillaries. There's higher amount of solutes in the blood, so water's constantly being pushed in. At the same time, water can be pushed out through the pores of the capillaries because of blood pressure. So you've got these two opposing pressures that are working against each other. Blood pressure trying to push it out, and osmosis trying to push it back in. So who wins? Well, I drew these arrows different sizes for a reason, representing the relative amount of force. At this end of the capillary, where blood is first entering, blood pressure is pretty high. That's on the side closer to the heart. And actually here, blood pressure is higher than osmotic pressure. So that is, blood pressure is pushing out, osmosis is pushing in, blood pressure wins. And so blood pressure ends up pushing water out. Now on the other end of the capillary, you've still got osmosis. That's working at about the same strength, but blood pressure has dropped. Which one looks like it's going to be the stronger force now? Kind of looks like osmosis is going to win the war this time, right? So down here on this end, water gets pushed back in. Why? It just does. Now there's some purposes to the water that gets pushed out into here, and we'll talk about where it goes later on and so forth. But there really is no real purpose. It's not like cells have to have you pushing water out and then reabsorbing it back into the capillaries. That's simply something that happens at your capillaries. First, the higher force of blood pressure pushes it out. Then the higher force of osmosis pushes it back in on the other end. Okay? So let me catch up in the notes here to what we were just talking about. All right? So down here at the arterial end of the capillary, the oxygen level is higher compared to the oxygen level out in the tissues. Same is true of nutrients. There's more nutrients in the blood coming into the capillaries compared to out here. And so oxygen and the nutrients are going to exit the capillary and enter the tissue cells due to diffusion and facilitated diffusion. At the same time, you've got that blood pressure trying to push water out and osmosis pushing it in, but blood pressure is the higher force down here, and so blood pressure ends up pushing some of that water out through those leaky capillaries. All right. So initially, there's a whole bunch of stuff leaving the capillaries. Oxygen going into the tissues, nutrients going into the tissues, water going into the tissues. How you doing, Kelsey? Good to go? Okay. Now, kind of down near the other end, the blood pressure has been reduced. We've gotten further away from the heart. We've gone through this big space in the capillaries, combined anyway. So we're further from the heart. We've got this greater combined cross-section area inside the capillaries, so blood pressure has now decreased so that it's lower than osmosis. And so osmosis now pushes the water into the capillaries. At the same time, we talked about how you've got more carbon dioxide and wastes built up in the tissues here and less in the bloodstream, and those things enter into the bloodstream and get picked up, and eventually they're going to go on back to the heart and lungs and so forth to be gotten rid of. Okay? So carbon dioxide and wastes enter due to diffusion. Either straight diffusion in the case of carbon dioxide or facilitated diffusion. All right? So your capillaries are very busy. Things are getting dropped off. Things are getting picked up by the bloodstream. This is the purpose of your whole circulatory, your cardiovascular system, being able to get oxygen and nutrients out to your cells, picking up all the wastes and eventually taking them to be gotten rid of, perhaps taking them to the kidneys to be filtered out, taking them to the lungs so you can exhale that CO2 waste or what have you. Okay? Any questions about how that works? Everybody understand? So you might see potential questions on the next exam. You know, which substances leave the capillary at the tissues? Which substances enter the capillary at the tissues? Why do these substances enter or leave the capillaries? Is it osmosis that was driving them? Is it diffusion that's driving them? Is it blood pressure that's driving them? So make sure that you understand what goes in and out and how it goes in and out. Okay? So here's this general picture here of blood coming in from an arterial into a capillary. Oxygen, nutrients, and other raw materials diffuse out into the cells. Carbon dioxide and waste diffuse into the bloodstream. Water gets pushed out, and then water gets pushed back in. By the way, a lot of the other components in blood, like a big old red blood cell, big proteins, antibodies, other components of the blood, white blood cells, and so forth, those are going to stay in the capillaries. Those don't get pushed out. They're way too big, so they stay in there. All right? Now, turns out that for this water that got pushed out here and then pushed back in, only about 85% of what got pushed out got pushed back in. That's actually, it ends up being several liters of water per day that is forced out and not forced back into the capillary. So the question is, what happens to all that extra water? Well, what would happen to you if nothing happened to that extra water? Your tissues would start to kind of balloon up with all kinds of excess water. You'd have gigantic arms and legs, and your body would be all swollen with all this excess water. It'd probably be actually pretty painful to have all that excess fluid in your tissues. So we got to do something with it. We have some capillaries lymphatic system that help take care of this problem. So the lymphatic vessels play a huge role in the immune system, and I'll talk about those in a few more weeks. But the lymphatic vessels also are important as part of the circulatory system. They have capillaries, roughly the size of the blood capillaries, and located in the same places as the blood capillaries. And they carry a fluid called lymph, which is largely the extra fluid from the tissues that's picked up by these lymphatic capillaries. So the lymphatic capillaries absorb that excess fluid that leaked out of the blood capillaries, that blood pressure pushed out, and that never got pushed back in because of osmosis. Eventually, these lymphatic capillaries join up with your circulatory system up in here, up near your heart, and so eventually all that fluid goes back to your heart anyway. It also plays a role as it picks up some of this excess water. It also ends up picking up invading cells like bacteria and so forth as well. And those little cells get taken into your lymphatic system and streamed past loads of white blood cells that look for foreign cells in your body and help get rid of them and start immune responses against them and so forth. So there's a little bit more going on than just picking up the excess fluids, but critically important. If we didn't pick up that extra water, we'd be in big trouble. All right. Everybody good to go? So here's a picture of where these lymphatic capillaries are in your body. They're these greenish things here. They look a lot like blood capillaries, although a little bit different. And we tend to have these lymph nodes. For example, you have concentrations of lymph nodes in your armpits and in your groin area and in your neck area. Sometimes when you have an infection in a lymph node, it feels swollen. So maybe you've had a sore throat and been able to feel the swollen lymph nodes in your neck before. So they play a big role in the immune system. But you can see that the lymphatic capillaries are also where the blood capillaries are, and they are able to pick up all that excess fluid. Okay? All right. So we're going to spend the rest of our time talking about the heart. We've talked about the blood. We've talked about the blood vessels. Now we're talking about the big old pump that moves that fluid through those pipes in the body. So the heart is largely, its most prevalent part is muscle, or myocardium. Myo means muscle, so myocardium is heart muscle or cardiac muscle. And humans have a four-chambered heart. Not all organisms do, not all animals have a four-chambered heart, but we do. So there are two chambers that are smaller called atria, and two larger chambers called ventricles. Atria are the entryways. Maybe you've been to somebody's house, or maybe you're lucky enough, maybe your parents have a nice house, but have you ever walked into a really nice house before, and they have a great big entryway that's like 2 stories high with a chandelier or something hanging in the entryway? Well, the formal name for those great big entryways is an atrium. And so atria are entrances to the heart. And since there's 2 atria, that means that blood enters the heart in 2 places. The ventricles are bigger chambers, and they're going to squeeze the blood out of the heart and out to other parts of the body. And then there is a wall down the middle called the septum that separates the right half of the heart and the left half of the heart. That is, blood actually can't directly go from the right half to the left half, or from the left half to the right half, without leaving the heart first. All right? So I'm going to draw a rather simplified version of the heart. This is not going to look very anatomically correct, but I think it'll help you understand how blood flows through the heart and through your circulatory system. So I'm going to draw the heart as a simple box. doesn't look anything like the heart really looks like, but it has the 4 chambers there, right? We've got 1, 2, 3, 4 chambers. Now, when you look at this heart, you have to imagine that this is somebody's heart in their body. So my right side is the right side of the heart, not your right side. And the left side of the heart is my left side, not your left side. So when you look at this as if you're looking at somebody else's heart. So the right atrium is this chamber right there. And the left atrium is over here. Okay. Then we've got these chambers at the bottom, which are the right ventricle. Oops, forgot an R in there. And the left ventricle. The wall in between right there, that is the septum that separates the right half and the left half of the heart. And you can see that there aren't any openings in that septum. There's no way for blood to go directly from the right side to the left side. It actually can do it by leaving the heart and then coming back in a different blood vessel. Now the heart also has 4 different valves that prevent backflow of blood. So we only want blood to flow in one direction. 2 of those valves are right here at the little entrance from the atria into the ventricles. And 2 of them are going to be right here at the exits to the heart. That is where the blood flows from the heart into its attached blood vessels, which aren't on there yet. The atrioventricular valves are the ones that are in between the atria and the ventricles. So here and here are where we would find the AV or atrioventricular valves. They allow blood to only flow from the atria into the ventricles. Blood can't go backwards, can't go from a ventricle into an atrium unless you have a bad heart valve, in which case you'll probably have to have surgery to correct it. But normally you can't get blood flowing backwards. Now there's also a valve here and a valve there at the exits to the heart, and they are called the semilunar valves. They do have more specific names to them. If you've ever learned names like the tricuspid and the bicuspid valve, for example, they are a little more specific, for example, for those atrioventricular valves. But just remember AV or atrioventricular valves. That's enough as far as I'm concerned. Okay. How you guys doing with the notes? Everybody got what they need? Chelsea, good? So here's a more anatomically correct version of the heart, and you can see that it actually looks like a traffic jam up there with all those blood vessels coming out the top of the heart, and that's partly why I draw it this way, because it's a little bit less confusing this way. But don't pay attention to the blood vessels for a second. Just look at the chambers of the heart. Here is the right atrium over here and the right ventricle. This is the one of the AV valves that's in between the right atrium and right ventricle. Here is the left atrium and the left ventricle. There's that other AV valve. And here are the semilunar valves actually at the exits of the heart. I'm going to draw them on the bottom of my simplified version, but technically speaking, they're at the top of the heart. Everything enters and exits from the top. It gets a little confusing, except for the inferior vena cava. Now take a look also at the walls of the heart. Which has thicker walls, atria or ventricles? Definitely ventricles, right? Look at the thickness of these walls down here. these chambers, the atria, only have to push blood from here to here. Not a very hard job. They don't have to be real thick and muscular. But the ventricles have to push blood out of the heart to other parts of the body. And so they have to be much thicker and stronger muscle. Okay? So we'll come back to the heart and the circulation in a little bit. Now, I mentioned that blood can't flow from the right side directly into the left side, and that's because the blood in the right side is not the same composition as what's in the left side. The right side of the heart pumps oxygen-poor blood that has just come back from your tissues. Remember we talked just a minute ago, let me go back to that picture we had a minute ago, right? The blood that's coming back from your tissues is going to be loaded up with carbon dioxide that it picked up from the tissues. It dropped off all its oxygen here, and so it's going to be oxygen poor and have a lot of carbon dioxide in it. All right? So blood first enters the right side of the heart when it comes back from the body, and it's oxygen poor. Lots of CO2, not so much oxygen. The right side of the heart is then going to pump that blood to the lungs, where it can get rid of the CO2, pick up new oxygen. Then it comes back into the left side of the heart. And the left side of the heart is going to pump the oxygen-rich tissue, blood, out to your tissues. That is, remember when we talked about this, we said the blood going out to your tissues has a high amount of oxygen and a low amount of CO2. So the general pathway is that blood goes from the right side of the heart to the lungs, to the left side of the heart to the tissues, then back to the right side of the heart again. So it's a continuous circuit. Okay? And as I mentioned, because blood from the right side of the heart can't mix with blood from the left side of the heart, it has to go out to the lungs before it can get back to the left side of the heart. Oxygen-poor blood doesn't mix with oxygen-rich blood. And so oxygen-rich blood gets pumped out to the tissues. What would happen if you had a hole in your septum? What do you think would happen if you had oxygen-poor blood leaking over here into the left side of the heart and then getting pumped out to your tissues? Would that be okay? Not so much. If you're not pumping the oxygen-rich blood out to your tissues, they need that oxygen. They're not going to be able to do that capillary exchange that we just talked about a little bit ago. So sometimes babies are actually born with a hole in the septum. Oftentimes it repairs itself within the first few months of life. It's not a real serious problem. Other times they may have to go in there and do surgery and actually repair that septum, because you don't want the oxygen-poor blood leaking over here and then get pumped out to the body. That's a problem. All right? So blood must go through the lungs to pass from the right side to the left side of the heart. Now, I've redrawn my heart here without all the labels to simplify things so you can see a little bit better. But I've got three areas here. We've got the heart, we've got the lungs, and we've got the body tissues. In this case, I drew a big toe. I know what we need. We need to give it some toenail polish. All right. So we're going to talk about the blood vessels that are attached to the heart and how the blood gets from one place to another. All right. So there are two general circuits or pathways that blood goes through. One is called the pulmonary circuit, and this is what we involve when we're pumping blood to the lungs. So the pulmonary circuit takes blood from the right side of the heart and sends it to the lungs. And there's two important blood vessels that we're going to be concerned with here, and they both have pulmonary in their names. So pulmonary always refers to lungs. The pulmonary arteries take blood away, right? Pulmonary arteries are going to carry the oxygen-poor blood out to the lungs. And the pulmonary veins bring blood back to the heart. Veins are going to bring the oxygen-rich blood back to the heart. Okay? So I can draw this